The product our group chose to analyze for both manufacturing and assembly is a generic 20 to 50 page stapler. The stapler is easily divided into two sub-assemblies, the first being the top sub-assembly, which houses the staples and driving unit. The primary task of this sub-assembly is to ensure that the cartridge of staples is always being pushed to the front of the stapler. This ensures that the driving mechanism of the stapler always has an object to perform work on while the cartridge is not devoid of staples. This sub-assembly also performs the task of driving a single staple through a material situated between the two sub-assemblies. The second sub-assembly is the base sub-assembly, whose significant features are the bending mechanism for the staple and the repositioning spring. The primary task of the base sub-assembly is to deform the staple being driven from the top sub-assembly. This deformation is achieved by the imprint on the metal plate that is positioned directly beneath the driving unit of the top sub-assembly. In common staplers, this plate has two imprints that the user can choose from. Each imprint directs the staple's legs in different directions. These two sub-assemblies are then attached together with a pin located at the pivot point of the stapling mechanism.
The base of the original part is made of a thermoplastic. This was likely injection molded, which would have a high startup cost in the tens of thousands of dollars range for the mold. Similarly, the upper casing of the part was also injection molded. This would need its own mold and would have its own startup cost in the tens of thousands of dollars range. The anvil, or metal base for the staples, is made of a flat aluminum metal. Likely, this would start with sheet metal that would be cut and stamped into a metal die to fit our mold. The half-inch metal spring between the anvil and magazine is standardized and can be purchased in bulk at around $2 each. Additionally, the 3-inch long compression spring that is used to push the staples out of the magazine is also standardized and can be purchased at around $1.53 each. The metal magazine is more complex and will require more steps to achieve tolerance. Likely, we would start with the sheet metal that would be stamped and cut to form the holes and edges. Next, this part would undergo additional stamping to bend the sides and front at 90-degree angles. The metal hammer would be formed similarly, starting with an aluminum sheet metal that is stamped and cut to form the edges and holes. The part would then be stamped into a die mold to form our desired curves and bends. The pusher could be made of plastic to keep costs down. This would likely be injection molded and made of thermoplastic. Because this part is not very complex, the mold would only cost a few $1,000s. Finally, the metal pin that is used to hold the stapler together is standardized and can be purchased in bulk. The original manufacturer likely made this part by cold drawing a stainless steel billet into a wire. In our new design for the product, we decided to modify the plastic injection molded casing that surrounds the stapler. Our new design would be one cohesive piece of plastic that would be connected at the end. This design will cut down the startup cost greatly because we will only need one mold for the casing as opposed to two in the original design. In this design, we will have to modify the plastic we use, as it will need to be elastic enough to bend at the axis.
Okay, so in DFA analysis, it's very important to eliminate any unnecessary parts. In the original document for DFA, we found a couple of parts that were not needed. For example, the case as a whole, it being two parts, could be simplified to one. There's also an extra spring that we didn't need, and of course a couple of extra components on the inside of the stapler. Redesign has, well, it's a couple less parts. It's now 75% efficient as opposed to the original design, which is about 66% efficient. So overall cost is going to go down for sure. All parts are used, therefore making the theoretical efficiency 100%. So as Daniel pointed out, the new redesign is going to have a similar manufacturing process. Since this is all ABS plastic, a good idea to do injection molding, as it would be very efficient, one of the cheaper options, and will not compromise on part functionality. So this is the final product.
our functioning prototype. Thank you for watching.